Recorded is rolling. It's Monday, August 29. So I have some graphs lined up for you guys today, and then I'm gonna solve some of these equations with you guys. We'll do some simplified versions of these equations because these are pretty all-encompassing. These are for linear motion. And then I will solve with you guys some problems from this page right here. So you guys remember your linear motion homework that picking up from you guys this Friday is whichever problems that I solve in class. So we should be able to do a couple of these scenarios today. Right? So just as long as you follow along, you'll be good there. And then on the back side of this page are 20 conceptual questions. We haven't done those yet. We'll eventually get to those. So just follow along as you go along, and then that's what I pick up from you guys on Friday. Okay. Now that'll help you out because I did over this last weekend write you guys your linear motion quiz. So I want to get that to you guys before the end of this week. I'm thinking Thursday probably. What I've done last couple of years, since the pandemic, is to issue a take-home quizzes. That's been working out pretty good. So I want to try that with this one too. And if I can, I'd like to get started on projectile motion by the end of this week. I don't know for sure that's going to happen, but we'll see. We'll see how this week pans out. Okay. I won't be here Wednesday. I always hate to miss school, but got stuff I need to take care of. So you guys got stuff on Wednesday. So there you go. Some stuff we're looking at here. All right. First thing, I've got a story for you guys that involves a dog running around chasing a squirrel. Chasing a squirrel. Okay. Now, where's okay? So we're gonna be doing some graphs here. Now, last week, one of the graphs that I did with you guys involved dropping a ball off the edge of a cliff. You guys remember that? Okay. And this is what displacement versus time look like. See how the ball's like spreading out. So as time passes, it goes further and further every passing second. That makes like a parabola shape. Its speed picked up at a constant rate, and that constant rate is free fall gravity. It's a type of acceleration, and acceleration would be constant. Right? You guys remember that from last week? So I want to do a set of graphs with you guys that's even simpler than this, that involves constant velocities. Okay? So let me get a picture going, then describe you guys a story, and then we'll make the same sets of graphs, x versus t, v versus t, a versus t, but for constant velocity type scenario. So I've got here a tree and a dog. Dog's just sitting next to the tree, just sitting there. Let's call that position 0. X equals 0 meters. Right? He's just hanging out there for a while, and then sees over here is this big bushy-tailed squirrel. It's like and then the dog takes off towards the squirrel, runs at constant velocity. Okay? Then we have the squirrel run back towards the tree and run up the tree, and the dog's going to chase the squirrel all the way back to the tree. Okay? So to spell that out, there's 3 parts to the story. The first part is the dog sits at rest for time 0 seconds to 10 seconds. So the first 10 seconds, the dog's just sitting at rest. 0 seconds is less than t is less than 10 seconds. Okay. Then the second part of the story, these are inequality signs. Those a little bit. Okay. Is that the dog runs toward squirrel at constant velocity. And this is for the next 10 seconds. So t is greater than 10 seconds, but less than 20 seconds. Okay. Let's call it the positive x direction. So put a little axis here, say the positive x direction. That's towards the squirrel. Okay. Then the third part of the story is the squirrel turns around, runs up the tree. Dog chases squirrel back to the tree at constant velocity. It's constant velocity. Okay. That's for the last 10 seconds of the story. So t is greater than 20 seconds, but less than 30 seconds. Well, inequalities. Okay. So there you go. This is the story. Okay. Now, when the dog changes his motion, say when he pushes off to start moving, and then when he turns around, there's brief acceleration, but the main parts of the story is that he's either at rest or he's constant velocity in the positive direction or constant velocity back towards the tree, right? And so that's gonna be like the main focus, right? Now let's set up some axes. We're gonna go x versus t, v versus t, and a versus t. Okay. So x in meters versus time in seconds. That's going to be just a first quadrant graph. Now the v versus t, meters per second and seconds. Okay. You guys see maybe like a sideways t graph? Okay. Do that for both the v and the a graphs. Okay. Make them like sideways t graphs. It'll make sense once the story unfolds. Acceleration, meters per second squared, time in seconds. Okay. I'll go ahead and throw some times on here. You got some intervals to work with. Say that's the 10-second mark, the 20-second mark, and the 30-second mark. So we got 0, 10, 20, 30, 0, 10, 20, 30, 0, 10, 20, 30. Okay. I'll define the initial position of the dog at 0.0. Well, actually, I said that right here. I said x equals 0 when the dog was just sitting there. So at time 0 is at position 0. Right? So at least give you guys that point. Okay. All right. So can you take this story and make these 3 graphs? Give you guys a head start. The way I'm going to put this together is I'll do all 3 graphs for the first 10 seconds, then all 3 graphs for the next 10 seconds, and then all 3 graphs for the last 10 seconds. Okay, so I'm trying to give you guys a head start here. If you guys can correctly beat me to some of these graphs, then that is a good indication that you know how this works. We haven't done anything quite like this yet, so take some critical thinking to figure this out, but I bet you can. Oh yeah.
If you don't mind moving
Good
the
story.
the second page over to the
Oh,
left.
this way?
Thank you.
Okay. Yeah. All right. Well, I remember what I did last week for dropping the ball was actually started with the middle graph, V versus T, and then I branched out from there. So I'll do the same thing here. Okay. Now, if the dog sits at rest for 10 seconds, then did you guys have this for V versus T for the first 10 seconds? You guys just did that, right? Okay. Okay. And then what about position versus time? So the dog started at 0.0. Hey, and if he's just sitting there at rest, is this position just not moving? So V0 position, right? About like that. Hey, what do you think the acceleration of the dog would be while he's just sitting at rest for 10 seconds? Also 0? Okay. So there you go. There's the first 10 seconds of each graph. So not too super exciting, but that'd be about what that is. Okay. Then the second bullet point. So between 10 and 20 seconds, now the dog is running, say, full speed towards the squirrel, just in a straight line. What does that look like? Ah, all right. I think you're on it. Okay. So Now, as long as it's moving at constant velocity, then velocity is constant. Okay. So I have to do something like that. Okay. Now, what about? Okay, you might say this. You might say, well, maybe he very quickly changes his velocity, so there's like a very steep line that connects those two. Right? No, whether they have that or not, because it's not a huge detail, but I guess technically it would be there, right? Okay. It's not vertical, but it's just very, very steep. And then what does x versus t look like during that time interval? Is he accumulating position at a constant rate? So wouldn't that have to look like that? Right? Picking up, right? Changing, so displacement is increasing at a constant rate. Okay. All right, now acceleration. This one has a little tricky part to it, but let me start with while he's in full sprint. Guys, while he's in full sprint, constant velocity. Guys, anytime you have constant velocity, what is your acceleration?
0.
0. So in the middle of his run, like at the 15-second mark, it would be 0 acceleration, right? In fact, this whole little segment right there is 0 acceleration. Okay. Now, is that true for this tiny fraction of a second around the 10-second mark where he goes from rest to being in motion? Okay, so at that point, for this tiny interval of time where he starts to get moving, he briefly accelerates, right? So I might put that detail on this graph by something like this. It's like spikes, right? Just for a fraction of a second. Okay. Oh, you know what I want to remind you guys about from last week too is the relationships between these three graphs, okay? Because there's relationships both ways. Okay. Let's go back and revisit what it looked like for dropping a ball, which is actually a little bit more involved, right? So do you guys remember that the slopes of the top graph tell you the graph below it? So slopes of x versus t tell you v versus t. Slope of v versus t tells you a versus t. Like v versus t had a constant slope for dropping the ball, and a versus t was a constant value, right? And then the slope for x versus t, see how like as you go left to right, if I hold my roller flush to the curve, it gets more and more and more steep. That's why velocity was increasing. It happened to be increasing at constant rate because x versus t was a parabola. This last week's stuff, dropping the ball, right? But that relationship exactly translates over here. So see how this part of the curve is flat? That's 0 slope. So velocity was 0. And then the fact that this one has 0 slope tells you acceleration is 0. Right? What about full sprint during this during these 10 seconds? Well, he was accumulating displacement at a constant rate. Look, rise over run. Isn't that slope rise over run? And isn't rise over run measured in meters per second? Rise over run, meters per second, which describes the velocity. And the fact that it's constant, hey, you get constant velocity. Look at there. Okay. And then if there's constant velocity, that means 0 change in velocity, which corresponds to 0 acceleration. Okay. Now, where there was acceleration briefly was where there was a change in velocity. Do you think that the slope would correspond sort of like the spike in the acceleration? Would. It was real brief, wasn't it? Okay. All right, then the last 10 seconds of the race. Well, I guess the race back to this tree, right? So they run back to the tree and they end up where they, well, the dog ends up where he started. Okay. So, did you guys get the last leg of this graph? These graphs? Maybe we'll go top to bottom of this one. Okay. Did you guys draw the graphs that the dog goes back exactly where he came from? Ends up where he started? He started at 0 meters from the tree. He ends at 0 meters from the tree. Okay. What about velocity versus time? Suppose the dog's running like full speed towards the squirrel and then full speed back toward the tree, maybe like 11 meters per second. This 11 meters per second positive. Do you think back towards the tree would be 11 meters per second, but negative? Okay, because it changed direction. Okay. Okay. Then I guess if I'm going to connect this a little bit so to make it look such a jarring jump. Okay, it's just a very steep connection between those two. And if it comes to a full stop, maybe a very steep connection here. Okay, not exactly vertical, but approaching that. Something like that. And then acceleration. Well, while the dog's running full sprint towards the tree, that's still 0 acceleration. Right? But if you wanted to, you could say that there was maybe like a spike in acceleration to get him turning around. Okay. And then maybe a final spike in acceleration as he comes to a dead stop right in front of the tree again. Right? Now, just like the slope of x versus t tells you v versus t, and the slope of v versus t tells you a versus t, you could also go from bottom to top. Do you guys remember what property of, say, a versus t tells you v versus t? So to do with the area, right? You guys remember areas? Okay. You guys remember like these rectangles are increasing at a constant rate, therefore velocity was increasing at a constant rate. Now this is for dropping a ball off a cliff. Well, let's see if the same pattern is true for the dog. Okay. Do you guys see like a change in velocity there? So suppose the dog sprints at like 11 meters per second. Do you guys see a change of 11 meters per second? Do you guys think that this little skinny triangle has maybe an area of, say, meters per second squared times seconds of like 11 meters per second? How about this? If the dog is going forwards at 11 meters per second and then makes an about face and now is running backwards at 11 meters per second, what is the difference between positive 11 and negative 11? And it's not 0. 22. Right. You guys see it? Do you guys think of this negative triangle? It has twice the area of either of these positive triangles? I bet they do. Okay. And then what about from V back to A? It's the same setup, right? So if this was like 11 meters per second times 10 seconds, that would be what, 110 meters? Do you think the dog would have accumulated 110 meters? And then this rectangle is negative, so he loses it all. These two rectangles cancel out. Dog ends up back where he started. You got it. Guess that. All right, so we got some graphs going on. Good. Right. You guys good on those graphs? All right. So those are, again, for a constant velocity situation, which is even a bit simpler than we did last week. But I do want you guys to also know, like dropping a ball from the edge of a cliff. This was in your notes from last week, so know this set of graphs. Okay. Let's solve some stuff. I want to solve some simplified, some questions that involve simplified versions of these formulas. Okay? Because think about what variables we're throwing around. There's 5 variables we're keeping track of. How much time has passed, t, how far something's gone, displacement x. There's initial velocity and final velocity. Okay? In fact, if something's changing velocity, like your guys' Hot Wheels cars were speeding up down the incline, there could be a bajillion different velocities. But notice in these equations, all you care about is starting velocity, ending velocity, right? Initial, final. Okay? And then finally, what's the acceleration? Okay, what's the rate change of that velocity? Okay? So those are the 5 variables: t, x, v naught, vf, and a. Okay? Those are the only 5 characters you see anywhere on that page. Okay? Those 3 equations will link everything together. But those are like the full versions of these equations. We can actually use simplified versions for simplified scenarios. Give you guys an example. Okay. So if you have constant velocity, then what do you know? How can you say that in physics? Because if you have constant velocity, then what is acceleration always equal to? 0. Then acceleration equals 0 meters per second squared. Okay. So let's think about what happens to these formulas for that condition, constant velocity. Okay. Let's look at the first one. Guys, if this a goes to 0, what do you have? X equals vt. Right? In fact, you can even drop the subscript because the velocity is not even changing. Okay. You could say this: displacement equals velocity times time. Okay. How about is that okay? Okay. How about the next equation? If this acceleration goes to 0, then doesn't this piece go to 0? And you just have, oh, look at that, final velocity equals initial velocity, right? Which makes sense. I mean, if you're not speeding up or slowing down, right, your velocity just stays the same, right? But it wouldn't really maybe be an equation you would apply. It would just be, okay, yeah, that checks out, not changing velocity. And the last one, if this a goes to 0, oh, well, it's kind of the same thing, isn't it? You just square root both sides, it says the same thing. Okay, so really, anytime you have 0 velocity, you're only ever using distance equals speed times time. That's it. Okay. So let's come up with 3 scenarios for this one formula, because as long as you have any 2 of these 3 variables, you could solve for the other one, couldn't you? Let's say scenario 1. Suppose that you're running with a velocity of 5 meters per second, and you do that for a time of 20 seconds. Okay. How far have you gone? Okay. And what's the answer to that? 100 meters? 100 meters? Okay. Try it. X equals v 5 meters per second times t 20 seconds. Okay. That feeds in. I see it just feeds in like that. Okay. Seconds cancel. Yeah, that's 100 meters. 100 meters. Scenario 2. Suppose that, so new scenario. Suppose that you run 400 meters in a time of, say, 8 seconds. What's your speed? Yeah.
3,000 to 1.
Be careful here. Right, so stress that. So x would be 400 meters. Actually, this is not even a realistic scenario. It'd be like,
15 meters.
yeah. Got it. 400 meters at some speed we're solving for 8 seconds. I see you could just divide both sides by 8 seconds. It would be 50 meters per second. 400 divided by 8. Yeah, that's 50. So v equals 50 meters per second. Meters per second, the unit. So right, that's a very tiny s right here. Okay. And the third question you could be asked is how much time has passed given x and v. Okay. So the third version of this, suppose that, okay, I got to run 800 meters, and I can run at a speed of like 5 meters per second. How long is it going to take me to get there? $160 seconds. There you go. Hey, this one I'm going to solve in terms of variables. Switch it up a little bit. Right, so solve for t, because it's only one algebra step. Right? You could plug in the numbers first. That's fine. Right? Or you could do the algebra first to come up with a general formula that you could apply for like anything you could plug in. Couldn't you just divide the v down and get x over v? Right? And then plug in the numbers after the fact? Didn't have to do it that way, but it's one way to do it. Right, the meters cancel, the seconds stack up on top, and yep, you get 160 seconds, which is like 2 minutes and 40 seconds, like that. Yeah, as long as you're going constant velocity, okay? Or maybe that's an average velocity. Okay, guys, good. Right, now, so that is one version of simplifying these equations, like these three equations. If acceleration is 0, then everything just boils down to that right there, and you're done. Okay. Let's do a different simplification. Okay. So another way to simplify these formulas, if you start from rest, for example, drop a ball. Whenever you see that word drop, that is one version of starting from rest, isn't it? Right? Start a car from rest, drop a ball. And what does that mean in physics? What variable am I telling you if you see either of those phrases? It means initial velocity is equal to what? Zero, right? Start from rest, drop a ball. Isn't initial velocity going to be just 0 meters per second? Okay. I wonder how these formulas are going to simplify if this v naught goes to 0. Right? Well, if this v naught goes to 0, doesn't this term go to 0? Doesn't that leave you with x equals 1/2 at squared? Is that okay? So I see that x equals 1/2 at squared. Okay. How about the next formula? If you start from rest, so v naught is 0, then isn't final velocity just equal to at? Final velocity equals at. Okay. I guess you could do the very similar thing with the last one. You could say vf squared equals 2ax. I'm not going to worry about writing that one down right now, but I'll take you guys through an example, and we'll bring up that third equation later and just see how it works out. Okay. So here's some simplified versions of those equations. Right? Well, if you start from rest, any version of that. Okay. Which actually, if you think about it, see, drop a ball. Where have you seen that? Ah, you did see that last week. You guys remember this ball being dropped off this cliff? Right? Initial velocity was 0 meters per second. Right. So actually, we've already applied the simplified versions to complete this entire table and these graphs. Right. I mean, this, if you're running, what do these look like on a table or on graphs? Boom, there's the answer right there in your notes from last week. Right. All right. So, how about this? Suppose that there's a cliff, height 125 meters. I have two questions. So if you drop a ball, then okay, so you drop a ball. How much time for the ball to reach ground? Let's say the valley floor. Okay. And the other question is, what is the crash speed? Like, how fast is that ball crashing into the valley below? Okay. Give you guys a head start there. So got a 125 meter tall cliff. You guys are solving that. We'll draw you guys a little picture over here. Here. How much time does it take for the ball to reach the valley floor? And then later on, figure out how fast is it crash landing into the ground. All right, anybody figure out how much time? Okay, let me start walking you guys through the, you guys know you can just use these formulas to answer everything, right? Okay. Oh, I did have to tell you guys something else though. This acceleration. You guys remember, we're talking about acceleration due to what? Due to gravity, right? Do you guys remember what free fall gravity is at the surface of Earth?
Okay.
About 10 meters per second squared. You would have to know that, right? Okay. Let me start walking you guys through the answer, and hopefully some of you guys are getting pretty close to answering it anyway. So if the height is 125 meters, isn't that like this x? So the has to change displacement by 125 meters. Changes at a rate of 10 meters per second squared. Okay. Can you solve for that t? Okay. let's do that. Okay, solve for that too. So x equals 1/2 at squared. We're going to go 125 meters. It's picking up at 10 meters per second squared. That's the rate that's speeding up. Okay? Does that for some time. And don't forget to square that. Okay, so we have to do a little bit of algebra here. Can I cross multiply the 2 and divide by 10? So 2 times 125 meters divided by 10 meters per second squared is equal to times squared. Now I'm one algebra step away from getting the answer. What's the last algebra step? How do you extract t from a square? You have to take the square root, right? Can you guys say that time is the square root of all this fun stuff? 2 times 125. Or if you just wanted a hard number for that, you could have done that first. But okay. So what's the square root of 2 by 125 on 10? That is 5. Okay. And the unit would be seconds. Meters cancels. Square seconds comes on top. Square root. It's seconds. 5 seconds. Okay. And the follow-up question is, what's the crash speed? I could call it VF, couldn't I? V sub F. Like how fast is the ball crash landing into the valley floor? Okay. Now you know it's been falling for 5 seconds. You also know this relationship. Here's how fast it's picking up as a function of time. Hey, can you pop in a 5 seconds right here? And 10 meters per second squared? You do that, right? Let's try that out. All right, we'll put it right here. So the speed it picks up to, as long as it starts from rest, is acceleration times time. We're doing 10 meters per second squared for 5 seconds. Seconds cancels. Well, one of the seconds cancels. Okay? Leaves you with meters per second. Hey, is that going to be 50 meters per second? Is that right? All right. Now, there's a reason that I picked this specific example with these specific numbers. Okay? And that's that. What is it? You guys remember Paul Hewitt from last week? Okay. This is one he actually solved backwards of how we solved it. You guys remember he gave you guys the story of you're with a friend. You walk into an old mine shaft. You're like, oh, I wonder how deep it goes. And you drop a rock. And you count to 5 before you hear the splash. So how deep is it? And you say, well, let's see, 5 seconds of falling. 5 and 5 is 25. 5 squared is 25. Half of 10 is 5. 5 times 25. It's about 125 meters deep. Gee, how'd you know that? College. You guys remember that? Okay, so we just did that, but backwards. Okay? He got 125 meters deep based on the fall time of 5 seconds. I told you the cliff height 125 meters. I said, well, how long did it fall for? But the answer is the same, still 5 seconds. Right? He went from here to here. We went from here to here. Right? But and we did a follow-up, which is we know the crash speed now for both this ball or his rock. Same thing. Okay? And you know what? These numbers here, falling for 5 seconds, it's picked up to a speed of 50 meters per second. 5 times 10 is 50. And it's also fallen 125 meters. Okay? That exactly matches your notes from last week. Look, drop a ball, 1, 2, 3, 4, 5 seconds. Picking up at 10 meters per second squared. It's picked up to speed of 50 meters per second. Bing! And it's fallen 125 meters. Bing! Look at that. Look at that. All right, is that right? So it all fits together. All right. Questions so far? All right, let's switch over to these questions right here. This page of questions. Okay. So remember, you guys just follow along with what I do in class. Whichever ones I answer class, as long as you do them also on your page, then eventually I'll pick this page up. And this week, you'll be good. Good to go. Now, there's 10 different scenarios here, and each scenario has a pair of questions. So let's get a big picture look of how this page is organized. Okay? hey, if you want to answer any of these kinematic questions, remember these, I should say linear motion, because we're answering just linear motion questions, might be moving forwards, and backwards, down, up and down, right? But we're just sticking on a single axis. Okay? I wonder how many pieces of information you have to answer anything. For example, if I say you're in a car and you're going at 25 meters per second, and then I ask the question, how far have you gone? Is that even an answerable question? You know, you're going 25 meters per second. How far did you go? Well, that's not enough information, right? Because you have to know, well, how long was I driving for? What's the time? Right? You might also have to know, is that a constant velocity or are you accelerating? Right. So there's not enough information to answer the question the way I phrase it. Okay? Guess how many of these variables you have to have at a minimum to be able to solve any linear motion question? You need to know three things, right? So for example, the car question, I gave you the speed. If you knew the speed and the time, you could answer it as long as you knew that there was constant velocity, which means zero acceleration. That would be three pieces of information, right? Boom, 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 right? Yeah, so you always have to have three pieces of information. Well, if you look at this this page, like for a bird's eye view, you guys see that every one of these scenarios, I give you guys a grid of those 5 variables, and I explicitly give you 3 of those. Okay? 3 here, 3 here, 3 here, right? 3 here. So everywhere I give you 3, right? Okay. Now, maybe that was a little too nice because a lot of textbook questions, some of these numbers are implied. For example, if anything starts from rest, you know, initial velocity 0. Or some of these say like a car brakes to a stop. And I explicitly gave you, well, that means final velocity must be 0, but you'd have to kind of figure that out. Right? Okay, but there we go. So you have 3 pieces of information. You can solve for the other 2. That's why there's a pair of questions per scenario, because I give you 3, you can solve for 2, right? Okay, so let's look at the first one. A baseball is thrown from the pitcher's mound, travels to the plate at approximately constant velocity. Okay. I should tell you guys too, this is the only one of these scenarios that I gave as a constant velocity. This to say 0 acceleration. Okay. Every single scenario other than the first scenario has some kind of acceleration. Okay. Calculate the time for the ball to reach the plate. Like what would the batter's reaction time have to be? Right. And also, what's the speed that the ball is crossing the plate? Let's answer those questions backwards, because I bet you guys can see exactly what the answer is to the second question already. Guys, the speed the ball's crossing the plate. If there's no acceleration, isn't it just the same as the speed that you threw it? Right? And if this guy throws the ball at 43 meters per second, shouldn't it cross the plate at 43 meters per second? Right? Or whatever number is on your paper. If your pitcher is throwing at 35 meters per second, then doesn't it cross at 35 meters per second? Okay. Is that okay? Okay. Because here's what we're saying. If this A is truly 0, if this A is 0 meters per second squared, then final velocity is initial velocity, right? It doesn't change because you're not speeding up or slowing down, right? Just constant velocity. Okay. So that's that one out of the way. Now let's go answer what's the batter's reaction time? Okay. Well, if there's 0 acceleration, remember just a few minutes ago, I was telling you guys this would be sort of a simplified scenario where, okay, you guys remember these notes from a few minutes ago? If there's constant velocity, 0 acceleration, it's just this. You guys remember that? Okay, because it's just this right here, right? So let's do that. Let's go. And I wanted to draw you guys a picture too. So we got a plate, we got the mound. Now the distance between the two, well, in American units, it's 60 feet 6 inches, but we're going metric. 18.4 meters, we'll call it 18.4 meters. Pitcher throws the ball. It's going at velocity of 43 meters per second, or whatever your number is. Okay. Hey, how much time does the batter have to react? Okay. So we're going x equals vt, right? Displacement equals velocity times time, and we're solving for how much time, right? I'm going to solve this in terms of variables because it's only one algebra step. I'm going to do the algebra before I plug in the numbers, is what I'm saying. Can you guys divide both sides by v and get the reaction time, regardless of the throwing speed, is always going to be x over v? Wouldn't that be true? Is that okay? So I'm doing the algebra first before I plug in the numbers. Plug in the numbers first, that's fine too. But I like this because now I have a general formula where here I can plug in any pitching speed and get any reaction time. So we're taking 18.4 meters divided by 43 meters per second. See what that is. I'm getting 0.428 seconds would be the reaction time. Okay. Meters cancels, seconds flips back up to the numerator. There you go. That's it. Okay. 0.43 seconds. Okay. Pretty good. That's right. All right. So you guys get on the first two questions then? Because that was number one. Number two is just velocity final equals velocity initial plus AT, but A goes to 0, so that whole piece goes to 0. So BF equals V naught. Okay. Next set. Actually, the next scenario is we're gonna skip that. Can I see number 5, number 6? Let's do number 5 and number 6 because it was a little simpler than 3 and 4. Okay. A ball is dropped from a treehouse. It reaches the ground in some given amount of time. Find the height of the treehouse and the speed the ball hits the ground. Hey, this sure does sound a lot like dropping a ball off a cliff, doesn't it? Okay. And in this case, it looks like somebody brought a stopwatch. And we're going to figure out how tall is this tree, is this treehouse. So 5 and 6 go together as a pair. 5 and 6. This will be the last scenario we have time for today. Okay, so we'll do this pair of questions and then that'll be it. Okay, so we've got a ball. We're going to drop the ball. Going to hit the ground. Okay. So we know the time to reach the ground, and we know acceleration, of course, and also initial velocity 0. And I want to figure out two things. I want to figure out what's the height of this treehouse. Call it X. Call it H or Y. I'll call it X. Okay. And also, what is the speed that this ball is crash landing, v sub f, like the final velocity? Okay. So I can use the simplified version because it's starting from S. X equals 1/2 AT squared. Right. Or sometimes you'll see it written this way. X equals 1/2 GT squared. Because G can represent gravity field, which is the type of acceleration. Right? Anything in free fall has that type of acceleration. Right? But the numbers, I know more often in this class than not, I use 10 meters per second squared. On this paper, I use the more precise values. So let's use that just so it matches with the multiple choice options. 9.8 meters per second squared. But 9.8 is so close to 10. Even if you use 10, you get close enough anyway. Okay. And remember, for this scenario, I said somebody brought a stopwatch. They say it took 0.9 seconds. Square that. Maybe they timed it like 3 times. It took an average because that'd be pretty fast time interval. That's what happened. Right? So let's see what this is. What is 1/2 times 9.8 times 0.9 seconds being squared? That is 3.97 meters. That's about a 4-meter tall treehouse. Pretty good. About 4 meters up. Okay. You guys good there? Okay. And kind of overkill here. I used this first equation and said V naught was 0 because started from rest, so it just boiled down to the simplified scenario that I wrote right there. Okay. The follow-up question, that's number 5. Number 6 says, well, how fast is the ball crash landing? And for that, could I use the second equation? Crash speed equals drop speed plus AT. Okay. So crash speed, or more simply, it's just AT or GT. Right? Remember I said G is a type of acceleration. So let's go 9.8 meters per second squared and do that for 0.9 seconds. Or whatever the number is on your paper, which is probably different. I'm getting 8.8 meters per second. Of course, that's ignoring air drag, which we always ignore in this class. So Now, let me do one last thing to round this up, because I could have used this third kinematic equation. Let me do this real fast at the sum before the bell. I could have said final velocity squared equals initial velocity squared plus 2ax. This goes to 0 because start from rest. Solve for VF. VF would just be the square root of, instead of 2ax, I'm going to say 2gh, because g is the type of acceleration. H could be the height of the tree, which is like x. Okay. Pop in this value for h, which we found. Okay, so what's the square root of 2 by 9.8 by 3.97? Okay. So square root of 2, 9.8, 3.97. This is some number of meters per second. Well, I know what the answer is going to be even before I hit enter. It has to be this, because there's two different approaches to get there, right? I hope it says 8.82. 8.82. That'd be meters per second. So it's the same thing, no matter how you approach it. Okay, so different ways to get there. All right, you guys good? Good for today. We'll continue this adventure tomorrow.